Okay, so in the previous slide we talked about why with the OR probability you have to subtract this portion that's counted in both the total of high school graduate and not a high school graduate. So notice the wording, what's the probability that the student is a high school graduate or owns a home? So that you want to sort of be looking out for the word OR. So when we find that out, if you have a table, it's easy to do. So you just add up what's in your table, 89 plus 221 plus 119 divided by the total of 500, which gives you 429 out of 550. Now, why can't we just do the following? So we know with OR probabilities, it means just add. Why can't we do the probability of a high school graduate plus the probability of owning a home? So here's high school graduate, 310 plus 340, which gives me 650 divided by 500. This doesn't work. Obviously, hopefully you've realized by now that probability is greater than 1, and probabilities can only be between 0 and 1. We only want the numbers highlighted in red as part of our answer. So if we add 310 and 340 together, we are counting that 221 twice. So we're going to come up with a formula we can use to make sure that we don't double count a number when we're talking about OR probabilities. So this means that this event is not mutually exclusive. So remember, mutually exclusive means they can't occur together. In this case, they do occur together. You can be a homeowner and a high school graduate. All right, so why can't we just use the general addition rule? We can't use the general addition rule for mutually exclusive events unless they have no outcomes in common. All right, so that's kind of an oxymoron, I guess. We can only use the addition rule for mutually exclusive events if they have no outcomes in common. So think about the sample space here. So this maybe is homeowners graduating from high school. This green area is counted in the yellow and it's counted in the blue. So if A and B are two events resulting from some chance process, the probability of A or B is the probability of A occurring plus the probability of B occurring minus the probability of A and B. So that's basically like saying, if you take a look at the previous slide, that is like adding this 310 plus the 340, but since this is counted twice, it's now subtracting it one time. We're subtracting the intersection, which then gives us just the three probabilities that we have here. Okay, so I would just remember that formula in general. A or B is probability of A plus the probability of B minus the probability of A and B. And if they end up being mutually exclusive, then this probability is going to be 0, but you're still using the formula every single time and remembering to get rid of what is counted twice. All right, so let's take a look at another one. The probability that you're a high school graduate or you own a home. Let's apply that rule here. So high school graduate is 310, own a home is 340, minus the intersection of both of those, which is the 221. When we do that, we end up with the same answer of 429 out of 500, or 0.858. We're basically taking that overlap and subtracting what was counted twice. All right, or like I said, if you have a table, you can just add them up, but if you want to use the formula, you always want to take out the and probability because it's counted twice. Now, Venn diagrams have uses in other branches of mathematics, but there's some standard vocabulary and notation that have been developed. So Venn diagrams can be really useful. Tables are one useful way for finding probabilities. Venn diagrams are another really useful way for discussing probabilities. They give us a visual way to figure out probabilities. Now, we talked about complements in previous slide. So if this is A, okay, remember the complement is everything not in A. So a little C means A complement, everything not in A. Here's A, everything not in A. Probability of rolling a sum of 5, not rolling a sum of 5. Okay, that's your complements. What would a Venn diagram look like if they're mutually exclusive? So remember, mutually exclusive events means they don't have anything in common. So here's the probability of A, here's the probability of B. They don't overlap, there's nothing in common. So this is like the probability of rolling a sum of 5, probability of rolling a sum of 6. There's nothing in common. You can't roll a probability of a sum of 5 and a sum of 6 at the same time with two die. All right, so what does it look like when we do have the intersection of events A and B? So what happens if they're not mutually exclusive? So the intersection of events A and B, notice that upside down U. I remember OR is the regular U and is the upside down U. That's the intersection. It's the set of all outcomes in both events A and B. Now, just remember for the or probabilities, or always means add, you're going to do the probability of A plus the probability of B. So it's like saying this whole event A plus this whole event B. But when I do A plus B, that's counted that green space twice. You want to subtract it once to get rid of the intersection. Okay? The union of events A or B is the set of outcomes in either A or B. So A or B is saying what's the probability of being a homeowner or being a high school graduate. So that's like saying I'm going to add these three pieces, but if you add high school graduate plus homeowner, then you're still counting that intersection where both of them occur twice. Okay, so A or B is like think of the table as adding the three separate pieces. One piece here, plus one piece here, plus one piece here. You don't want to count that middle section twice. All right, so just to keep the symbols straight, remember U is for union or. The upside down is for intersection with an N for the word and. So and is the intersection and U is the union. All right, so how's the AP exam formula sheet going to help you? They will give you this formula right here, so you'll have to know that for any event A or B is the probability of A plus the probability of B minus the probability of A and B. So they will give you that formula, so just know that that's on your formula sheet to make use of during the exam and all your tests and quizzes that you have. All right, so let's go back to the example where we talked about pierced ears. So how can we use a Venn diagram to display the information and determine the probabilities? So let's say that A is male and B has pierced ears. So we're looking at male and pierced ears. How could we make a Venn diagram that would represent that situation? Now, notice the total of male is 90. So A is representing 90, but I have 71. That doesn't really make sense, okay? That's just the males that don't have pierced ears. But keep in mind, this intersection right here is the probability that they are male and have pierced ears. So there's that 19. So the Venn diagram kind of breaks it up. So this 19 belongs to the fact that they're male, and it belongs to the fact that they have pierced ears. So the 71 plus the 19, that's all in yellow, has to give me that total of 90. Now think about that being counted twice. It's counted once in the yellow, so now it's being counted in the blue in the fact that they do have pierced ears. So take a look over here. Here's the fact that they do have pierced ears. 19 is male and pierced ears. There's my intersection. Plus the female 84. That's just females, not male, for a total of 103. So that 103 is made up of both pieces within that blue, 19 plus 84. And I would suggest when you're making a Venn diagram, always do that middle intersection first, so you know that this total has to be 103. Take out what's and then you'll know what you have left over that's not within the intersection. Okay, so just take a look at the symbols here. Male and pierced ears is A and B. Okay, so that's in this green section right here. Inside circle A, so this is inside circle A, and outside circle B. So this is all of A, but outside circle B. So that's kind of a little tricky here. So how would I write that in symbols? Male is A, that's all of A, and there's my intersection, and outside of circle B. So B complement, so think about B is B, everything outside of B is B complement. All right, so you don't include that 19 here because that 19 is still included in B. We want inside circle B, outside circle A. So inside circle B, okay, is everything outside. Okay, inside circle B is circle B right here. Sorry, I was reading the first piece first. Okay, inside circle B. Outside circle A is A complement. So let's think about this. What is inside of B and outside of A? So we start out with inside of B. Okay, so we kind of shade that in. Outside of A, we kind of completely take A out, so we're just left with the 84 because that 19 is still within A. What's outside both circles? All right, outside both circles, okay, is male and no pierced ears, because remember, A is male and B is pierced ears, so the opposite of male is female and the opposite of pierced ears is no pierced ears. So A complement everything outside of A and everything outside of B. All right, so here's a two-way table summarizing. We're going back to the example with the high school graduate and not high school graduate. Summarizing using symbols once again to take a look at being a high school graduate and being a homeowner. So if we want to break this down, the intersection of the two circles right here is G and H. So that is high school graduate right here and a homeowner. Graduate and doesn't own a home. How would I write that? So that's G and H complement, because we defined H to be a homeowner, so doesn't own a home is everyone that doesn't own a home. So we want G and H complement. So if I'm going to shade this in, I'm going to shade in all of G, and H complement, I'm going to shade in everything outside of H. So I don't want this piece right here, this 221. I don't want this 221, so just the 89. You say, well, why don't I include the 71? Because it has to be inside of G, okay? Not a graduate, but owns a home. So they're not a graduate, so it's G complement, so it's everything outside of G. So I'm not going to include that here. Everything outside of G is just the 119. And owns a home, that's just the 119. Not a graduate and doesn't own a home, okay? So that's G complement, everything outside of G. H complement, doesn't own a home, everything outside of H, that's 71. All right, so just to go ahead and take a look at this is sort of an interesting question. We're going to see how Venn diagrams are actually the most useful whenever we're discussing percentages. So according to the National Center for Health Services, in December 2012, 60% of U.S. households had a traditional landline, 89% had cell phones, and 51% had both. Suppose we randomly select a household in December 2012. We want to construct a Venn diagram to represent the outcomes of this chance process. So anytime that you see percentages and you see the word and, so had both, that's the word both here, so the and probability, I would highly suggest drawing a Venn diagram. From that Venn diagram, we can then find the probability that the household has at least one of the two types of phones, and the probability that they have a cell phone only, and the probability that they have neither type of phone. So it's going to be much easier to find from the Venn diagram. All right, so let's see what those answers look like. So draw your Venn diagram, making sure you know what each region represents. Always start in the middle when you're making a Venn diagram, because remember that when you're starting in the middle, this whole circle, the whole yellow circle, has to add up to your landline. This whole purple circle has to add up to the total of cell phones. All right, so the entire blue circle has to add up of cell phones, which is 89%. We know that 51% own both. So if I do 51 plus 38, that gives me the 89. And then for the landline, we know that 60% own landlines, 51% own both, and just 9% only have landlines. So keep in mind that the whole Venn diagram should add up to 1, and the 0.02 represents the probability that they have neither a cell phone or a landline. So what's outside the Venn diagram plus what's inside the Venn diagram should always add up to 1. All right, so how could we do that? How could we use that to find the probabilities? Find the probability that the household has at least one of the two. So remember, at least one is the same thing as 1 minus the probability of having none. So outside the Venn diagram is 0.02, 1 minus 0.02, that's having neither a cell phone or a landline is 0.98. Or just add up everything in your Venn diagram. I always suggest when the question asks for at least one, always do 1 minus the probability of none. Otherwise, you have to add up the probability of the landline, plus the probability of cell phone, plus the probability of both. That can take more time when the problems get more complicated. Find the probability that they have a cell phone only. So that's in the portion of the Venn diagram that has no intersection, okay, and that's 0.38. And like I said, once you have your Venn diagram, it's really easy just to see and pick out your answers. Find the probability that the household has neither type, 0.02. We already decided that was everything outside the Venn diagram. All right, so probability problems often involve simple calculations you can do on your calculator and not show any work. Don't be tempted just to write down the answer. If you write down a naked answer that is one that shows no work, you're not going to receive credit on the full or on the free response portion of the exam. Please make sure you include the probability statement, the fraction if possible, there's not always a fraction, and then your decimal answer. How do you know when to use a Venn diagram versus a two-way table? Venn diagrams work best with percentages, especially when they're not mutually exclusive and the problem states the and probability. If you have percentages and they give you an and probability, use a Venn diagram. Just remember to fill in the overlap and portion first.